This fluid mechanics lecture is focused on interphase transport. Topics include friction factors, flow through tubes or pipes, flow around objects, and flow through packed columns. Consider the use of dimensional analysis and experimental data to develop correlations, which can be used to solve flow problems, leading to approximate engineering calculations that are useful for solving many practical problems in various areas of engineering. These correlations and this type of analysis are especially useful for complicated flows and geometries, such as flow through a packed bed, which has many applications in catalysis and reaction engineering. There are two broad categories of engineering correlations. One is flow through channels, and two is flow around submerged objects. Flow through channels is relevant to things such as pumping liquid through pipes, extrusion of plastics through dies, etc. Flow around submerged objects pertains to things such as the motion of air around a car or airplane, sedimenting particles, or flow around tubes in heat exchangers. This can also be extended to flow through packed beds. The typical objectives of engineering analysis are either one, to relate the flow rate to the pressure difference. This can be either the mass flow rate, W, or the volumetric flow rate, Q, or two, to determine the drag force, Fd, from the approach velocity, U infinity, for flow around an object. So two examples are shown on the right. The first is flow through a pipe. We have mean velocity U, sometimes also designated by V in angular brackets, meaning the average velocity. It could also be a little case u in angular brackets, also denoting average velocity. The other case is flow around a sphere. U infinity is the velocity far upstream of the sphere or other object before the presence of the object influences the flow. So the velocity is essentially uniform from left to right, far upstream of the object. In each case, the force exerted by the fluid on a solid surface, which is designated by F sub F arrow S. This is the force the fluid exerts on the solid, hence the notation. This can be decomposed into the sum of two components. One, F sub S, is the force from the fluid even if there is no flow. For example, force due to pressure in hydrostatics, as we've discussed previously. And the second component is F sub K. This is the additional force due to fluid motion. The K arises because this is a kinetic energy force, essentially, or at least that's what's used in the textbook. Now it's important to note that F sub K acts in the direction of the mean flow. So for example, flow through the pipe flows from left to right. Fk, the force the fluid exerts on the wall of the pipe, will be then from left to right in the direction of the fluid flow due to the frictional interactions, in other words, the shear stress of the fluid on the pipe walls. For flow around an object, F sub K is in the same direction as U infinity, the flow far upstream of the object. In this case, it's from left to right. So the force due to fluid motion on this object is from left to right. It tries to push the sphere to the right, as one would expect from basic intuition. We have focused mostly on exact solutions to date. For turbulent flow or for complicated geometries, exact velocity and pressure profiles are difficult or impossible to calculate. Therefore, from here on forward, we will focus on approximate solutions based on data from careful experiments and applied to geometrically similar systems through correlations based on dimensionless variables. We've discussed dimensionless variables in great detail in our lecture on dimensional analysis and order of magnitude approximation. So, when we're looking at the force on a solid due to fluid motion in any of these correlations, we designate the absolute value or the magnitude of the force F sub K due to fluid motion as just scalar Fk as the product of three factors, A times K times lowercase f. Here, A is a representative area for the system, we'll make specific in a moment. K is the kinetic energy per volume of the flowing fluid, and F is what's known as the friction factor. So this equation here defines the friction factor. So the force the flowing fluid exerts on the solid is equal to the representative area multiplied by the kinetic energy per volume multiplied by the friction factor. And so this is how F is defined for any type of fluid flow, internal or external. So in the case of flow in channels or conduits or pipes, the area is the wetted surface area. So this is the area of the solid in contact with the fluid. For example, it's the surface area of the pipe. So the pipe has length L and diameter D. It's pi d times L. Pi d gives the perimeter, pi d L gives the perimeter times length. This is the area of the pipe wall in contact with the fluid. The kinetic energy term is 1/2 rho times the average velocity squared. This V in angular brackets is the average velocity of the flow through the pipe or channel or conduit, as we've designated here. Now for flow around a submerged object, the definition of the area is different. In this case, it's the projected area perpendicular to the approaching flow. So if one has flow past a sphere of radius r, the projected area is a circle of radius r. And so the area is pi r squared in that case. And so it's projected area perpendicular to flow for external flows, whereas for internal flows, it's the area of the solid in contact with the fluid. The kinetic energy term is the same, 1/2 rho times the average velocity squared. In this case, for flow around submerged objects, the characteristic velocity u infinity is the approach velocity of the fluid far upstream of the object, where the velocity is assumed to be uniform. So looking at the first case, flow in channels or conduits or pipes, we have our correlation as shown here. This is the general case. The force that the flowing fluid exerts on the solid is the area times the kinetic energy term times F. We defined A, K, and the average velocity V. So we have our circular tube, and the mean velocity of the fluid in this tube we're calling capital U. It can also be V in angular brackets. This tube has diameter D, has length L, and so the force Fk acts on the walls of the tube in the direction of the bulk flow. This would be the shear stress integrated over the surface area of the solid in contact with the fluid. So by definition, if we substitute the area here, the area is pi dl as we mentioned, so we have a pi dl term for Fk. Kinetic energy term is 1/2 rho times the average velocity squared. This term here is also the average velocity as we had before. So if we want to make this more precise, we can type in the average velocity like this to use the same notation that we have below. So we have the 1/2 rho v squared term here for kinetic energy multiplied by F. We can also perform a force balance on the fluid that's located between two planes in this tube. So first we can take the left-hand side, we can say let the z coordinate be equal to 0 at this point here. So if we come over here, we can say let this be equal to z equals 0, and we can let the right-hand side then be z equals L. So if we do a force balance in the fluid between these 2 points, we can look, and the contribution here would be the normal stress. Normal viscous stress will vanish, or at least will be very small compared to the pressure contribution. And so the force balance in the fluid between these 2 points is basically the difference in pressure between z equals 0 and z equals L multiplied by the cross-sectional area of the pipe. So the pressure difference would be P naught minus PL multiplied by pi d squared over 4. So the force on the left-hand side is P naught times pi d squared over 4, and the force on the right-hand side of the fluid, which would be acting towards the left, would be PL times pi d squared over 4. We take the difference, and we have another expression for the force on the fluid. We can now combine these 2 equations, essentially equate these 2 equations. And so what we get is that F sub k, which we have here, is equal to pi dl multiplied by 1/2 rho times the average velocity squared times f, and that's equal to what we have on the right. We have the difference in pressure, so the dynamic pressure at z equals 0 minus the dynamic pressure at z equals L multiplied by pi d squared over 4. So we can simply cancel out a factor of pi from each side, get rid of 1d here, cancels this d here, and then we can solve this equation for the friction factor F. And what we find for flow through pipes or conduits or channels, friction factor F is equal to, we have 1/4 here. We're left with D divided by L, so we get D over L. And then now we have the pressure difference term, P naught minus PL, divided by this kinetic energy term, 1/2 rho multiplied by the average velocity squared. And so this F is called the fanning friction factor. And as we see, it can be calculated directly from experimental data. So we can measure the diameter and length of the tube. We know the density of the fluid. We can measure the average velocity, and we can either measure or control the pressure difference applied across the tube. Hence, we can find this very easily from a series of experiments. So here's the equation written a little bit more neatly for the fanning friction factor. Now, in general, we can show by dimensional analysis that the friction factor F is a function of the Reynolds number. So for Poisson flow, or fully developed laminar flow in a circular tube, the friction factor is simply given by 16 divided by the Reynolds number. And we can solve for that from this equation by substituting. We can get an expression for the pressure difference in terms of the mean velocity from Poisson's law, substitute into this expression here, rearrange and get a Reynolds number to come out of it, and we saw that the friction factor is 16 over the Reynolds number for fully developed laminar flow in a circular tube, which corresponds to a Reynolds number less than about 2100. For turbulent flow, we have to use experimental data to determine F. There's no simple solution that's the analog of the Poisson solution. So one convenient formula, for example, is known as the Blasius formula, after one of the famous researchers into fluid mechanics and turbulence. In this case, the friction factor F is 0.0791 divided by the Reynolds number to the 1/4. And this correlation is accurate if the Reynolds number lies between about 2100 and 10 to the 5. Now, there are other correlations listed in Bird-Stewart-Lightfoot section 6.2, or you can look at figure 6.2-2. So, for example, here's the figure. This is a plot of the friction factor as a function of the Reynolds number. And we show here is the laminar regime corresponding to Poisson flow. F is 16 over the Reynolds number. Once we arrive at about 2100, there's a transition, and the laminar flow solution is no longer stable. It's unstable, and it jumps to turbulent flow. And so it jumps to one of these curves listed here. Now, hydraulically smooth corresponds to a perfectly smooth wall of the pipe. This is what we use if we don't have any other information about the pipe wall. If one has a rough wall, so for example you have flow through concrete tubes or channels or something like that, this K over D is a measure of the characteristic length of the wall roughness divided by the diameter of the tube. So the larger the value of K over D, the quote rougher the tube is. And this roughness introduces additional friction as it interacts with the fluid. Essentially, the more rough the wall is, the more area there actually is with all the little nooks and crannies and crevices where the fluid contacts a solid, And so there's more fluid in contact with a solid, a greater surface area due to the roughness, and this creates additional drag or additional stress that we find manifested in a higher value of the friction factor. So one way to solve problems like this, if you're given the Reynolds number, you can simply look up and find, corresponding to however rough the tube is, or if it's perfectly smooth, go from the Reynolds number, let's say 10 to the 5, up to this curve here, and then we move directly to the left and we read off a value of something like 0.004 for the friction factor. You can see this part here of the hydraulically smooth curve corresponds to that Blasius formula. So it's essentially a fit to this curve that was determined experimentally. And there are other correlations listed in the text that are valid for larger ranges of the Reynolds number, or also for tubes that might be more rough. So once again, this is figure 6.2-2 in Bird, Stewart, and Lightfoot. Now, oftentimes in turbulent flow, we might have to deal with a non-circular tube. And so a very useful and a very important concept is the idea of the hydraulic radius, designated as R sub h. Now, hydraulic radius is the ratio of the cross-sectional area of the channel or conduit, which is designated by S, to the wetted perimeter. This is the area of the wall of the tube or channel or pipe in contact with the fluid, and that's designated by Z, the perimeter. So the hydraulic radius is the ratio of the cross-sectional area to the wetted perimeter. And so what one would do is, as a non-circular tube, is simply to replace the diameter of the tube, D, for a circular tube, by 4 times the hydraulic radius in a correlation. Well, why is it 4 times the hydraulic radius? It just happens to be that if we were dealing with a cylinder, then the hydraulic radius is 1/4 of the diameter. So, for example, we'd have RH is equal to the cross-sectional area, so we'd have pi d squared over 4 divided by the wetted perimeter, which is pi d, and so we have d over 4 for a cylinder. So to recover the traditional result, we simply take 4 times the hydraulic radius, and that would recover the diameter in any correlation. And so that is the origin of this 4 RH being equal to the diameter in the correlation for turbulent flow. This does not work for laminar flow. Laminar flow is highly dependent on the exact geometry of the tube. Turbulence, because there's a lot of cross-stream mixing, there's a lot of motion perpendicular to the walls that sort of spreads the momentum out more uniformly over the cross-section of the tube. This hydraulic radius idea is relatively accurate for turbulent flow. It's not accurate for laminar flow, so we only want to use the hydraulic radius for non-circular tubes for a turbulent flow. Another example, let's say we have a square tube. Tube has length of each side as A. What is the hydraulic radius? Well, for this thing here, the cross-sectional area is simply A squared. The wetted perimeter Z is equal to 4A. Consequently, RH is equal to A squared over 4A, which is equal to A over 4. So basically, we want to replace the diameter in a correlation for turbulent flow by the side length A for a square channel or a square tube. So hydraulic radius is a very important concept. This will come up again as we deal with macroscopic balances and the mechanical energy equation when we're dealing with chapter 7 in a couple of lectures. So it's very important to keep in mind the definition of the hydraulic radius and how it's used. Basically, 4 times the hydraulic radius is equivalent to the diameter for a circular tube. Okay, next we'll go over an example that would apply one of these correlations. It's what's the pressure drop that's required to maintain a given flow rate through a tube. So in this case, a liquid flows through a horizontal tube It's horizontal, so we don't have to worry about the effects of gravity on the flow. And the tube has diameter of 3 centimeters, and the mass flow rate is W, is 1,028 grams per second. The liquid has density rho is 0.935 grams per cubic centimeter, and the viscosity mu is 0.00195 Pascal seconds, which are the SI units for viscosity. We're asked two questions. One, is the flow laminar or turbulent? And two, what is the pressure drop, dP/dz, or the pressure gradient, along the tube that's required to maintain this flow rate? This is something very useful in an application. It would help one size the pump power requirements required to maintain this flow. So you can take a few minutes and think about this, pausing this video, and then you can resume and we will discuss the solution. All right, so let's reconsider this example and solve it. So the first question is the flow laminar or turbulent, or can we not tell? Well, the way to figure out if the flow is laminar or turbulent is to calculate the Reynolds number and see if it's larger or smaller than the critical value of about 2100. So the Reynolds number is defined as rho d multiplied by the average velocity divided by viscosity, but we don't know what the average velocity is for this system. We are, however, given the mass flow rate, W, and W is equal to the product of the cross-sectional area of the tube, which is pi d squared over 4, multiplied by the average velocity multiplied by the density. Consequently, we can see that the average velocity of the liquid through the tube is equal to 4W, 4 times the mass flow rate, divided by pi d squared rho. And we can substitute numerical values here. So we have 4. The mass flow rate would be 1.028 kilograms per second, and we divide this by pi. The diameter is 0.03 meters squared, and then the density, 0.935 grams per cubic centimeter, corresponds to 935 kilograms per cubic meter. And so what we find here is that the mean velocity of the liquid through the tube is 1.555 meters per second. Now, it's not necessary to convert everything to the SI units and then multiply through as we did here. It's a very effective approach if you like it. Another way to do it is just to use the units given. You can do this in centimeters, grams, second, CGS system if you like. So now we have the mean velocity, and so we can simply come back over here and substitute it into the Reynolds number. So the Reynolds number, we have 935 kilograms per cubic meter multiplied by 0.03 meters multiplied by 1.555 meters per second divided by the viscosity. Viscosity is 0.00195 kilograms per meters times second. So we can just recall here that 1 Pascal is equal to a Newton per meter squared. And so a Pascal times a second is a Newton per meter squared times a second. And Newton is going to be kilograms meters per second squared. So we multiply that by seconds per meter squared, and what we get is kilograms per meter second as the SI base units for 1 Pascal, which we have here in the Reynolds number. So substitute this in, and we find the Reynolds number is approximately 22,400, which is 2.24 times 10 to the fourth. And so is this laminar turbulent flow? Well, this is greater than the critical Reynolds number, which is about 2,100. And therefore, we have turbulent flow. So anytime one has to determine whether the flow is laminar or turbulent, simply compute the Reynolds number and then see if it's greater than or less than the critical value. The critical value of 2100 for the transition from laminar to turbulent is valid once again only for flow through a cylindrical tube. For other systems, the transition could occur at different values, and we'll have to look up the reference values of when that actually occurs. All right, so we know the flow is turbulent. Next question is, well, how do we figure out the pressure gradient? What we can do is we can use the definition of the friction factor that has been added here to this slide on the top right. So recall F is 1/4 d over L, the pressure difference over 1/2 rho average velocity squared. So we can solve this equation in for P naught minus PL over L, which is equivalent to minus of the pressure gradient, in terms of the friction factor d and 1/2 rho v squared. We know the average velocity now. We know the density. We know the diameter of the tube. The only thing we don't know is the friction factor F. We do know, however, that the friction factor F only depends on the Reynolds number. So we know that friction factor depends on Reynolds number. So once we've computed the Reynolds number, as we have here, we can simply evaluate the friction factor using any of our favorite correlations. So let's do that. We can use the Blasius formula, for example. It's convenient and it works for this range of Reynolds numbers. Blasius formula is accurate when Reynolds number is between 2100 and 10 to the 5. We have 2.2 times 10 to the 4, so it lies within that range, and this is a very simple one to use. So Blasius formula F is equal to 0.0791 divided by Reynolds to the 1/4. And if we substitute here, you would get 6.468 times 10 to the minus 3. So now we have F. We could also say, well, our Reynolds number is 2.2 times 10 to the 4. So we can look at this plot. We have 10 to the 4, we have 2.2 times 10 to the 4 gives us right here. So if we go over here, we can estimate it would be approximately 0.064 or 0.0065. So you can always read off from this chart, if you like. It gives a very quick, rough estimate. You can get a more accurate value by simply inputting one of the correlations. And so I kind of like to do it that way. But if you're doing a very approximate, crude first pass analysis, it might be simpler sometimes just to read it off this chart. You could also use a different correlation listed in the text. For example, the Prandtl formula listed in Bird, Stewart, and Lightfoot gives a value of F of about 5.96 times 10 to the 3. So it's different by approximately 10%. You can also use the Barenblatt formula, which gives 6.44 times 10 to the minus 3, much more in line with the predictions listed here. Any of these formulas, however, will have a margin of error of probably 5 to maybe as much as 10%. So any of those values would be perfectly fine for these calculations. When doing these engineering calculations, first pass, 10 or 15% accuracy or error is probably the best one would hope to get. And so any of these values would be perfectly fine. I like de Blasier's formula when it applies. I always want to make sure, of course, the Reynolds number lies within the range of validity of the formula. In this case, Reynolds number is 2.24 times 10 to the 4th. That's less than 10 to the 5th, and so de Blasier's formula is perfectly accurate. All right, so now we have the friction factor F determined from this. And what we can do is we can rearrange this expression, the definition of the friction factor for flow through a tube, to find the pressure difference. So doing that, we see that the pressure gradient, or actually the negative of the pressure gradient, minus dP dz, which is equal to P naught minus PL over L, because dP dz is PL minus P naught over L. In this case, we're doing it the opposite way. P naught's greater, and so dP dz is negative. The pressure always decreases in the direction of flow, so minus dP dz is actually positive. So P naught minus PL over L from this formula here is equal to 4 over the diameter multiplied by the kinetic energy term, 1/2 rho times the mean velocity squared, multiplied by the friction factor F. And so now we simply substitute values. We have 4 divided by 0.03 meters, multiplied now by 1/2 times the density, which was 935 kilograms per cubic meter. And then we multiply by the mean velocity that we found on the previous slide, 1.555 meters per second. And we multiply by the friction factor, which is this value here. And if we evaluate this, we find that the pressure gradient is 975 kilograms per meter squared second squared. And we say, okay, let's make these units into something that's a little bit more meaningful. So we can group this into kilograms times meters per second squared, which is a Newton, times 1 over meters squared times 1 over meters. So why would we do this? Well, this then gives us Newton per meter squared per meter. Newton per meter squared is a Pascal, which is a unit of pressure. And so we say it's 975 pascals per meter. So let's say dP dz is equal to minus 975 pascals per meter. So the pressure drops by 975 pascals per meter length of the tube. Now you don't have to do this final analysis here. You could leave all this as kilograms per meter squared second squared, but it's often good to check the units, make sure it comes up with something that makes physical sense. In this case, units of pressure are pascals, so it changes by a pressure unit per distance along the pipe or tube, which is exactly what we want. So that's a very simple example of how to apply these correlations to find the pressure drop required to maintain a given flow rate, and it illustrates the use of the friction factor quite nicely. All right, next we can move on to flow around objects, or external flow. So flow around a submerged object, we have the same main definition of the force due to fluid motion, Fk. It's an area times kinetic energy term times friction factor. The difference now is A is the projected area perpendicular to the approaching flow. It is not the surface area of the object. So for example, flow around the sphere is illustrated here to the right. The projected area of the sphere in a plane perpendicular to the oncoming flow, so that's going to be this up and down plane here, the sphere looks like a circle to the flow in front of it. And the area of that circle is pi r squared, or pi d squared over 4. So that's the area that goes into this definition of the force the fluid exerts on the solid. If the Reynolds number is very small, we're in the Stokes or creeping flow regime, then F is equal to 24 over the Reynolds number. If the Reynolds number is larger, less than about 6,000, F is approximately the square root of 24 over the Reynolds number plus 0.5407 squared. This is essentially a fit to experimental data. It's taking this Stokes law result that one can derive exactly using the Stokes law solution for flow past a sphere at vanishingly small Reynolds numbers. That's the 24 over Reynolds number. They add this little correction term and try to do a curve fit, which is where this expression comes from. The other interesting thing is that the friction factor is roughly constant at a value of about 0.44 over a very large range of values of the Reynolds numbers, between about 500 and 10 to the 5. And so anywhere in that range, we can simply take this constant value, if we like, to approximate what the friction factor is. So if we look at the curve of the friction factor versus Reynolds number, it looks something like this. And we have this both for smooth or rough spheres. So we have this essentially linear regime on this this log plot. And this regime here corresponds to the Stokes solution over there, which is more accurate even for small Reynolds numbers out here. Then this expression here works up to Reynolds number of about 6,000, which would be over here. So this whole curve part corresponds to this expression. Then we see this large range from about 500 or 1,000 all the way up to 10 to the 5 for a smooth sphere. The Reynolds, or the friction factor, is roughly constant at a value of about 0.44, which is this last result here. We see a couple of interesting things, however, on this plot. One is there's this very rapid decline in the friction factor once the Reynolds number exceeds a certain value. And eventually it starts to grow back up as Reynolds number increases further. However, what it implies is that if one's going at a certain velocity, if the velocity increases a little bit more, the friction factor and therefore the drag on the sphere will drop suddenly for a particular value of Reynolds number. So some sort of transition that's occurring here that's causing this very rapid change in the friction factor for Reynolds numbers of about 5 times 10 to the 5. The other thing that's interesting, though, is that for a rough sphere, this transition occurs for a smaller value of the Reynolds number. Now, this rapid dip in the friction factor, or drag force or coefficient, as the Reynolds number increases for flow past a sphere, is known as Eiffel's paradox. Eiffel being the person who designed the Eiffel Tower in France. Now, a similar phenomenon occurs for flow past other objects. So even for flow past a cylinder, one would find something similar occurring for a different value, but still different value of the Reynolds number, but a very qualitatively similar phenomenon. So the question is, why does Eiffel's paradox occur? So here's the example once again. We have our smooth sphere. We have, for a larger range of Reynolds numbers here, this is the Stokes regime here, 24 over Reynolds number. And then we get this approximately flat range, about 0.44. Then we have this dip for Eiffel's paradox. Then we have this dash curve here now is for a smooth cylinder. You can see it's qualitatively similar. There's actually no creeping flow solution for flow past a cylinder. That satisfies all the boundary conditions, so there's no analog of the Stokes result over here, but the behavior is still rather similar. And then we also have this rapid dip once the Reynolds number exceeds a threshold value corresponding to Eiffel's paradox. So the question is, why does this occur? So what sort of transition is causing this behavior to happen? And from what we've seen before, the kind of transition that happens is the transition from laminar to turbulent flow. So that seems to imply it has something to do with that. So here's the exact detail. For flow past a sphere, an adverse pressure gradient develops near the object. So an adverse pressure gradient is a pressure gradient that's in the opposite direction of the main flow. So in this case, flows from left to right. However, near the surface of the sphere, the pressure is such that the pressure will now increase as one moves from the front to back of the sphere. So inertia is carrying the fluid from left to right. Near the surface of the sphere, the pressure gradient is trying to push the fluid from right to left. Consequently, as the pressure is pushing against the fluid, the fluid decelerates and loses momentum in a thin region near the surface of the object. Eventually, the fluid loses all of its momentum and it starts to flow in the opposite direction due to the pressure gradient. So right near the surface of the sphere, there will be flow from right to left instead of left to right as in the main flow. This is known as flow reversal. Once flow reversal happens, we have what's known as separation. The streamline will separate from the surface of the object, leaving downstream a wake. A wake is a pronounced region of disturbed flow due to the presence of a non-streamlined object. So if the boundary layer, which is a thin region near the object, is laminar, so recall from our very brief discussion of this previously, for high Reynolds number flow, we can neglect viscosity over most of the flow. So away from the object, the flow is dominated essentially by inertia and pressure. However, near the surface of the object, viscosity is important and allows us to apply the no-slip boundary condition. And so viscosity is important in a very thin region known as the boundary layer. And the thickness of the boundary layer decreases as the Reynolds number increases. It's proportional to Reynolds to the minus 1/2. We'll derive this towards the end of the class when we talk about boundary layer theory. So if the boundary layer corresponds to laminar flow in this thin region near the fluid, well, laminar boundary layer has less momentum near the wall than a turbulent boundary layer does. In turbulence, there's greatly enhanced mixing due to the random motion of the flow, and so there's always a motion from away from the flow, away from the object towards the object. This movement and mixing in this direction for turbulent flow replenishes the momentum near the wall. So the boundary layer, the velocity profile, is much flatter for turbulent flow than it is for laminar flow, just like we saw for flow through a tube or a pipe. The cross-stream mixing due to the turbulent fluctuations smooths out or enhances momentum transfer perpendicular to the wall, and it smooths out the velocity profile. So a laminar boundary layer has less momentum near the wall than a turbulent boundary layer does. Consequently, this adverse pressure gradient that's pushing from right to left near the surface of the object will stop or decelerate and stop the fluid from moving in a laminar boundary layer much more rapidly than it would for a turbulent boundary layer. So a turbulent boundary layer will persist for a longer distance, even if the pressure gradient is in the opposite direction, because the fluid will decelerate more slowly due to the increased momentum in the turbulent boundary layer, plus the replenishment of the momentum in the turbulent boundary layer by mixing with the faster moving fluid further away from the object. So in other words, the laminar boundary layer will separate much earlier, much further towards the front of the sphere than the turbulent boundary layer will. So the wake, the region of perturbed flow behind the smooth sphere, will be much thicker than it will for the turbulent boundary layer case, where the separation occurs at a larger distance downstream, further towards the back of the sphere. So reduced pressure losses in the wake lower the drag and the friction factor. So this wake really disrupts the flow. It has a major effect on the pressure distribution all throughout the entire flow regime, and this formation of eddies, which are regions of circulation or vorticity that move through in this wake. So this effect on the pressure is a major contribution to the drag, or the force the flowing fluid exerts on an object for non-streamlined objects when wakes form. So why do we show this for a golf ball, where it's smooth versus rough? Well, what also happens is that the laminar to turbulent boundary layer transition occurs when Reynolds number exceeds a threshold value, the critical Reynolds number REC. If the surface is rough, this perturbation to the flow lowers the critical Reynolds number. So a rough surface, like this rough golf ball, will have a turbulent boundary layer for a smaller value of the Reynolds number. So if we go back to this plot here, we see that we need a Reynolds number about 5 times 10 to the 5 to get in this decreased friction regime for a smooth sphere. For a rough one, it can be a factor of 5 or 8 smaller. And so what this means is if one's hitting a golf ball, a lot of people can't hit the golf ball at a high enough velocity to attain this Reynolds number for a smooth sphere. However, they can hit it in this range of Reynolds numbers, and therefore when the golf ball is rough, the drag is going to be much lower than it would be if the golf ball were smooth, and the golf ball is going to go a lot further. So you get increased range on your drives or other strokes by using a rough golf ball versus smooth. And there's other reasons for the roughness as well, but this is a simple fluid dynamical reason for it. couple other notes. When we're talking about wakes and forces of fluids on objects and drag and things like that, there are two contributions to the drag. One is known as the frictional drag. This is due to friction between the fluid and the surface. It's essentially the integral of the shear stress over the surface area, also known as viscous drag. Frictional drag is associated with the development of boundary layers along the solid surfaces. It's dominant for attached flows. So attached flows are one where there's no separation. That occurs for a streamlined body. So think of an aircraft wing, or an airfoil, or something like that. So you streamline an object to try to prevent this flow separation from occurring. In that case, you don't have this big disruption to the pressure in the wake region, and the total drag is basically due to the friction of the fluid flowing over the surface. And so the frictional drag is related to the surface area exposed to the flow. The other type of drag, the other contribution, is known as pressure drag. And this arises from eddying motions, these circulating motions, the vorticity, set up in the fluid by the disturbance caused by the object. So when a wake forms, you get these eddies that form behind it. This modifies the pressure distribution throughout the flow, and in particular over the surface of the object, and this then increases the drag as well. You have to integrate not only the shear stress, but also the pressure over the surface to find the total force of the fluid on the object. So pressure drag is also known as form drag or profile drag. As I mentioned, it's associated with the formation of the wake, the region of disturbed flow downstream of the object. It's dominant for separated flows. Separated flows are when wakes occur. Boundary layer separation, you get the wake, and the perturbation of the pressure in the wake causes this additional contribution to the drag. This separated flow occurs for a blunt body. So things like cylinders and spheres are blunt. They're not streamlined. And this is related to the cross-sectional area of the object rather than the surface area exposed to the flow. So finally, we'll illustrate this with a real-life example. Here's flow past a ball. This is an image showing the disturbed flow in the boundary layer. This is a case where it's in the wake. This is a laminar boundary layer. We have a large wake. In this case, they use a tripwire upstream to transition the flow from laminar to turbulent. So we have a turbulent boundary layer. You can see with the turbulent boundary layer, the flow separation occurs much later because the momentum can be maintained more in the boundary layer. The pressure that's pushing back this way doesn't cause the flow to stop and separate as quickly as it does for the case of a laminar boundary layer. And so we have a much smaller wake as shown in this actual image behind the object, which is completely consistent with the schematic diagram shown in this previous slide. So that's schematic. This is actual pictures from experiments. Finally, we can talk about the third part of this lecture, which is friction factors for flow through packed columns. This slide gives a few examples of packed columns. We can see shown here, you could have trays for the packing, or you could have random packing, which is a bunch of oddly shaped things thrown in together, or you can just have random packing of things with the same shape, like spherical particles. So you have a tray or some sort of thing to hold the packing in place. In this case, it's metal trays with the packing. This middle one here is a schematic of a distillation column. You'll talk about this a lot more in the separations course. In this case, you're putting vapor from the bottom up, liquid from the top down, and you're trying to get good contact between the liquid and vapor to get good transport of mass, good separation of a phase from one to another. And in this case, it shows an example of structured packing, which would be maybe steel trays with metal pieces going all across. The idea is to try to increase the contact area between the two phases, liquid and gas in this particular case. It can also be for single phase. You can have reactions occurring at the surface of the packing for heterogeneous reactions. Or you can also have adsorption or things like that, where you can have either a pure liquid or pure gas flowing through the column in contact with a solid adsorbent. So structured packing in this case would typically be these trays. Shows random packing here, which is a bunch of things just thrown in to the column. Here's another example here. You have a support plate to hold the packing in place, a bunch of packing material dumped in, and another thing on top to prevent it from moving around. And here's an example of an actual picture from experiments, a bunch of strangely shaped things constituting the packing in this packed column, and you'll have either a liquid or gas, some sort of fluid moving through this packed column. Now, these packed columns are extremely common in chemical engineering practice, whether it's distillation, whether it's reaction engineering, any sort of separation process. And so being able to calculate the flow rate from a given pressure drop or the pressure drop to maintain a given flow rate in these packed columns or packed beds is something that's very important for chemical engineers to be able to do. So the first thing I want to do is introduce some terminology for packed columns. So the first thing is this epsilon. Epsilon is known as the void fraction. So it's the volume of the voids, that's the things not occupied by packing, divided by the volume of the bed. So 1 minus epsilon is the fraction of the volume of the tube or bed occupied by packing material. Epsilon is the fraction that's not. It's the fraction available for flow. So it's basically the air spaces or the spaces between the solid particles comprised or caused by this packing. This little a is known as it's a parameter that's the ratio of the wetted surface area to the volume of the bed. So it tells you how much surface area per volume you have. So if you have a given volume of bed, you can figure out how much surface area there is for contact between the solid packing and the fluid. Another thing that's used is known as the specific surface. It's a sub v. It's just a ratio of the parameter a to 1 minus the void fraction epsilon. So it's a ratio of a to the fraction of the bed filled with solid particles or solids. And the mean particle diameter, dp, this would be the diameter of a spherical packing material. It's for non-spherical, it's equal to 6 divided by AV. And if we substitute the definition for AV, it's 6 times 1 minus epsilon divided by A. These are just things you can look up in the text in chapter 6.4 anytime you need them. Something that's very good to be aware of, though, and to understand what it means is V naught. It's known as the superficial velocity. It's the ratio of the volumetric flow rate to the cross-section of the empty column or tube. So this is also the ratio then of the volumetric flow rate Q to the cross-sectional area S. Volumetric flow rate is mass flow rate divided by density, so it's W over rho divided by S as well. Physically, what is a superficial velocity? Well, it will be the average velocity of the fluid in the absence of packing. So if you have a given flow rate through this tube and the tube were empty, you could figure out what the average velocity is, and that's what's known as a superficial velocity. Because in reality, with this packing here, the actual velocity of the fluid is considerably higher than the superficial velocity because the area for flow is reduced by the packing. The fluid has to move through these tiny crevices, the tiny spaces between the packing material, and so the cross-sectional area, or the area for flow, is much smaller than the total cross-sectional area of the tube. The average velocity is much higher than the superficial velocity. However, if one wants to compute things like the mass flow rate or mass flux through the tube, the superficial velocity is a very useful thing to use because that tells you on average how quickly the fluid is moving up through this packed column. So the mass flux is designated G naught. It's a product of the density and the superficial velocity. It's also a ratio of the mass flow rate to the cross-sectional area, or the density times the volumetric flow rate Q over the cross-sectional area. As we said, S is a cross-sectional area of the column, pi d squared over 4 for a circular tube or a cylindrical column of diameter d. As we've seen earlier in the course, W is the mass flow rate and Q is the volumetric flow rate. So mass flow rate would be things like kilograms per time, mass per time, volumetric flow rate, things like meters cubed per second. So there are three main correlations one would use to relate the pressure drop to the flow rate or flux through a packed column. For laminar flow, we have this correlation here, minus the pressure gradient is equal to P naught over PL over L. So this assumes the pressure gradient is constant throughout the thing. We have steady flow. And it's 150 mu times the superficial velocity divided by the particle diameter squared times 1 minus epsilon squared over epsilon cubed. Now, it's important to keep in mind the limits of validity. This requires the void fraction to be less than 0.5. And requires this dimensionless parameter dp g naught over mu times 1 minus epsilon to be less than 10. So you always want to check, either before if you can, or after doing a calculation with a correlation, that these constraints are met so that the correlation actually applies to the regime you're looking at. For highly turbulent flow, we have this correlation here, which is valid if this thing is greater than 1,000. So that's for very large values of the flow rate. And then we have a hybrid correlation, which basically is a fit to these two things in experimental data for points that lie between. This is known as the Talmadge equation, and it's valid for a large range of dp g naught over mu times 1 minus epsilon, lying between 0.1 and 10 to the fifth. If it's smaller than 0.1, one would use a correlation for laminar flow. If it's greater than 10 to the fifth, you have to try to look something else up, but it's kind of rare that it will be bigger than this. Final comment here is if this final term, which varies, is just made a constant value of 7/4, then this hybrid correlation becomes what's known as the Ergun equation. That's more well known than the Talmadge equation, even though they're sort of contemporary. And the Ergun equation is very commonly used. You'll see it a lot in the literature. It simply is taking this last term, replacing with 7/4, which is a constant, instead of this term, which varies with the mass flow rate. Mass flow rate also then varies with the velocity. All right, so let's see how we would actually apply this in practice. Let's estimate the void fraction of a packed column. So we have an example taken from the book. It's problem 6A.6 in Bird, Stewart, and Lightfoot. We have a tube of a 146 square inch cross section and 73 inches in height. It's packed with spherical particles with a diameter of 2 millimeters. Pressure difference of 158 psi, pounds per square inch, is maintained across the column. Liquid of viscosity 56.5 centipoise and density 1.2865 grams per cubic centimeter flows through the column at a mass flow rate of 244 pound mass per minute. I want to determine the void fraction of the column. We can see right away the first impediment here is we have a big mixture of units. We have English units, we have SI units, we have other things as well. So what we want to do first is convert everything to consistent units and then figure out which of the three correlations on the previous slide we can apply depending on the values of epsilon and dp g naught over mu times 1 minus epsilon. So let's identify the various parameters. So we have 146 square inch cross section. This tells us that S is equal to 146 square inches, which, if we convert it to square centimeters, is 941.93 cubic centimeters, or square centimeters, sorry. Let's fix that. All right, the length of the column L is 73 inches, which is equal to 185.42 centimeters. The packing diameter, dp, is given to us as 2 millimeters. We'll convert that to centimeters as well. Use the CGS system, so 0.2 centimeters. We have the pressure difference. We have P naught minus PL is 158 psi. And if we convert that to CGS units, we will see this is equal to 10,893,716.5. A few too many significant figures here. Dynes per centimeter squared. Let's say, well, what's a dyne going to be here? So we put this in bracketed units, and this is actually grams per centimeter times second squared. Now we have the mass flow rate, W. W is equal to 244 pound mass per minute. And we can convert that to 1,844.61 grams per second. So 1.8 kilograms per second. And the mass flow rate is the product of the mass flux G naught and the cross-sectional area S. So we can then solve this for G naught, which appears in the correlations. And G naught is equal to 1.9 0.583 grams per centimeter squared second. And then finally we have the viscosity. Mu is equal to 56.5 centipoise, which is of course 0.565 poise, and that's equal to 0.565 grams per centimeter second. So we have a lot of conversions to do here. Finally, we have the density as well. Density is given to us in good enough units already. So the density rho is equal to 1.2865 grams per cubic centimeter. So the first thing here, of course, like we've done, is we identify each of these values with the particular variable that it corresponds to for this system. And we converted everything to a consistent set of units, the CGS system in this case, centimeters, grams, second. Next thing we want to do, in order to figure out the void fraction, is to figure out what correlation applies. So we want to estimate the key parameter that appears in all of these correlations. So we want to estimate dp g naught over mu times 1 minus epsilon. And so this is equal to 0.2 for dp. G naught is 1.9583. Mu is 0.565. Times 1 minus epsilon, and so we get 0.6932 divided by 1 minus epsilon. Now we were asked to find epsilon in the void fraction in this problem, so we can't substitute it in. But what we can say here is that dp g naught over mu times 1 minus epsilon is going to be less than 10 as long as epsilon is less than 0.931. And it's essentially impossible to get a void fraction of 0.931 with packing, because you wouldn't have enough stuff to hold the packing in place. There wouldn't be enough contact between the particles. And so packing is always going to be more dense than this. So what we're going to do here is assume that epsilon is less than 0.93. And the maximum value of epsilon is 1 for an empty column. But let's assume it's less than 0.93. And so we can use this basic correlation for laminar flow right here. If epsilon, well, we'll assume further that epsilon is less than 0.5, so we can use that correlation. And if epsilon is less than 0.5, then this dp g naught over mu times 1 minus epsilon will certainly be less than 10. Then after we finish the result and calculate epsilon, we can go back and check if these two constraints are indeed met. So let's use this correlation then for laminar flow. So we can say now that from this here, P naught minus PL over L, so the pressure difference is 10,893,716.5. The length of the column in centimeters was 185.42, and that's going to be equal to, from that correlation, 150 times, well, viscosity in the CGS units is 0.565. That's multiplied now by V naught over dP squared. V naught, if we go back to our previous thing, we don't have the velocity, but the velocity is equal to, well, let's say this, not the velocity, but we can say that the G naught is equal to the average velocity, or actually in this case, it's equal to the superficial velocity, V naught times rho, we're trying to write here. So the superficial velocity V naught is simply equal to G naught over rho. And so G naught, if we have from the previous slide, is 1.9583. So that's the value we want here. .9583 divided by now the density. Density is 1.2865. So that's G naught over rho. That gives us then the V naught for this term in the correlation. Then we divide by the particle diameter squared. It's 0.2 squared. And then this is multiplied by 1 minus epsilon squared over epsilon cubed. And so if we insert the numbers and do the calculation, we find that 1 minus epsilon squared over epsilon cubed is equal to 18.2167, and so consequently we find that epsilon is equal to 0.300. And so now we can check. It's less than 0.5, yes. And we can go back and check what our other parameter here, this dp g naught over mu times 1 minus epsilon. So once we have this value, we see that dp g naught over mu times 1 minus epsilon is equal to, we found before, 0.6932 divided by 1 minus 0.300, and this is equal to 0.99, which is less than 10. And epsilon 0.30, which is less than 0.5. So both constraints for this correlation have been met, and this is an accurate value. So that works perfectly fine. Or you could say, well, let's just use the Talmadge equations. That's valid for any of these values of epsilon or this other parameter. And so if we were to use the Talmadge equation, we would find that epsilon is 0.302. So that's consistent with our use of the correlation for laminar flow. So either the correlations could be used and we get the same result in each case. So that completes this lecture on interface transport and the use of friction factors for some basic engineering calculations. We'll move on in the next lecture to talk about macroscopic balances, integral equations for the conservation of mass and momentum for systems of engineering interest.